It's feeling good. We're recording the session, and first I'll start by asking if anyone has questions from 2 days ago. Are there any questions, any areas that were not clear? I hope we were able to get some of the slides and go through them just to be sure everyone understood what we discussed. Yeah, so last week, like after the introduction class, we kind of started with basic stats. We discussed a bit what statistics was, the different areas of application. We talked about descriptive statistics, inferential statistics, data types. We introduced some fundamental concepts as well, talking about population, what a sample is, an observation. We talked about sampling and why we described some of the basic sampling methods, simple random sampling, stratified sampling. Today we'll build a bit on some of the things we saw not last week, 2 days ago. We talked about some other fundamentals, what bias is, what a variable is, a statistic, how data is organized in tables. We defined some of the concepts around tables, variables, and talked about relational tables a bit. Then we talked about missing values because it's something very common in data that you have to deal with most times. We talked about outliers, and we'll see some more interesting ways to identify and deal with outliers today. But yeah, so we'll go over some very fundamental things, mostly like high school stats, just to bring us back up to speed. And in practice, many of these things are used. And also, it also helps kind of to discuss the applications as well of the different concepts and the ideas we'll be touching on. So firstly, descriptive statistics, like we said 2 days ago, one of the first things we look at is measures of center. So with descriptive statistics, what we're trying to do is to describe data or events that have happened in the past, right? To get useful information, useful insights. It could be trends, it could be relationships, correlations, statistical associations, whatever the case is. Descriptive statistics is describing data that we have, describing a process or an event that has happened, right? And with measures of center, we're trying to find that midpoint, right, that's representative of the entire data. And the very first and most common statistic that comes to mind would be the arithmetic mean, which, is obvious, we know what it is. So bar X is just the sum of all your individual observations. Remember, observation, sample, population. So the sum of all your individual numerical observations divided by the number of observations there are, right? So it's just your straightforward average. And what I tried to do was just put like the formula in Excel, like what keyword you would use to compute whatever statistic we're discussing in Excel, just for ease of implementation for those that want to try things out. And what's important to note about the arithmetic mean is, so I just put a picture underneath that shows a graph. It's just data points, right? X and Y axis, and you see that green line. So that green line represents the mean. What's important to note about the mean is the sum of all the deviations around the mean is 0. And please, in today's class, like if you're lost in anything I say or you're not following, like just stop me, just drop something, the message, just say repeat or explain or something. So I'm not just going ahead, right? So what we mean by sum of deviations around the mean is 0 is if the mean is the green line, in this case 2, right? If you look at each data point's distance from the mean, so in the first data point here is 1, and here we're looking at, let's say, the values on the y-axis, right? So it's 1 here. The second data point is 2. That's the y-axis value. Third is 4. So if you look at the distance of the first from the mean, which is 2, so it is -1, 0, plus 2, -1. So when you sum all the distances from the mean, the sum of those will be 0. In other words, you have as many points, the total distance of the points that are greater than the mean and the points that are less than the mean gives you 0. So it's that midpoint such that the deviations around the mean is 0. It's really important to understand the arithmetic mean in this way, because when you're using it in practice, you need to know what it's trying to measure. So it's giving you that midpoint on your x-axis, for example, in this case, for your data. So it's distributed around this whole spread, and the green line or your arithmetic mean gives you the middle such that the distribution is 0. For the geometric mean, this is just a kind of mean where if you look on the right-hand side, so x bar g is just the multiplication of all the individual data points, right? And then the nth root of the number of observations. So if you have 3 observations, 5, 6, and 9, the geometric mean will be 5 times 6 times 9 and the third root. So raised to power 1/3, right? And some of the useful applications of the geometric mean are when you're finding an average of rates, right? As in the case of like interest rates, for example. So in finance, like you have some interesting applications, and I gave one example underneath. Nothing to dwell too much on. For the harmonic mean, which I'm sure we're familiar with, is just the inverse of the weighted inverse of each of the data points. So 1 over sum of 1 over each observation. So it's just an inverse arithmetic mean and inverse completely to reverse it. And this is usually useful. If you remember, for those that are like engineering or science students here, you remember how you sum the resistance of like parallel circuits, right? Circuits in series resistance, you just add each resistance. And when it's in parallel, you do like 1 over and sum, and then reverse like the inverse of that sum. So the benefit here is just it helps in applications where in finance, for example, you're trying to calculate average rate of return when you're dealing with different rates of returns, right? For different investment periods, when the investment periods are not consistent. It has lots of different uses, right? In economics, for ratios. And so the kind of measure of center would depend on the application, right? Also, when you're doing the average of speed, for example, because the weight of your speed, right, is relative to the distance, right? So if you have a faster speed, then it's a shorter distance. So you shouldn't just average. If you drove for 100 kilometers per hour and then 80 and then 40, you're not just doing a straight average, right? Because where you drove faster speed, arguably the distance covered will be more for the same time. So if you remember, I hope I'm not stretching this too much, but if you remember when you did like little problem solving around speed, a lot of the approach you were using was harmonic means. So it's just 1 over first observation plus 1 over second observation, and then that sum, and then 1 over the entire sum. So it's as straightforward as that. And in Excel, like anyway, you just put equals to har mean, and that's it. Weighted mean. So with the weighted average here, you're assigning weights, and the weights could be assigned for different reasons, right? So it could be, so for example, there's a typical calculation in credit cards where you're looking at interest. You want to get the average interest rate on a portfolio of different kind of credit cards, right? So different interests apply to balances. So for someone with a large balance and a small interest rate, and someone a portfolio that has small balances but large interest rates, right? You cannot just pick the interest rates and find the average, because you need to weight it to the balances, right, within the portfolio. So there are different cases where you want to attach the numbers that speak to the importance of each of the components of a certain distribution for which you want to get the mean. And so your weighted mean is just some product of the weight times each observation, and you're summing it, and 1 over the number of observations. So all this is like really straightforward stuff. I'm sure we're all familiar with it, just to refresh us, right? So everyone good so far? I'll take silence as a yes. So just remember, the thing to take away from here is when you're presenting the mean of, your data, the mean of a column in your data, the mean of a variable, you have to think about what you're saying, right? So if you're saying the average of these numbers is this, like, why are you showing the average? What does the average mean, right? And that's why I give some business examples. And what kind of mean you use depends on what message you're trying to pass across. And another thing we're going to look at down the line is why using just the mean most times is not enough. You have to usually use the mean with a measure of variability, but we'll get there. Like, if you just say the mean, you could have 10 numbers that are less than 10 and have one large number that's 1 million. And it's going to drag the mean all the way like out, right? So that mean, is it really significant, right? If you had 10 customers such that 9 out of them had last month sales less than $1,000, and 1 person bought something of $2 million, right? Your average is going to be somewhere close to $1 million, right? So if you just presented the mean of sales, so our average sales last month was about $1 million, does that really give a good picture of the average sales of each of your customers? Not really, right? Because you have a huge outlier. So I want us to start thinking, like, when we're going through all these statistics, don't just say, oh, okay, I remember this thing from secondary school. This is how you calculate average. This is how you calculate Joe mean. No, I want us to always be thinking about, in practice, what does that mean for a data analyst? What does that mean for a data scientist? What does that mean for someone working with business data, right? So the scenario I just gave, case in point, right? If you're showing the mean, you usually want it to go with another statistic, which we'll discuss, that shows the dispersion within the data. But anyway, for the mean, arithmetic mean is this, geometric mean, harmonic mean, weighted mean. If we're all good, like, let's give some thumbs up. So I just need to know, like, everyone's on the same page. Someone's hands up. Go for it. Someone laugh. Where are they laughing?
Can you hear me? I'm not good, sorry. I don't know what harmonic or the weighted mean. Can you go over those two again, please?
Absolutely.
Thanks.
Okay. Right. So with the harmonic mean, you're doing a mean such that for each observation, you're just doing the inverse of the observation. So let's say we were to find the harmonic mean of 2, 5, and 6, right? The harmonic mean of 2, 5, and 6 would be first the sum of the inverses. So 1 over 2 plus 1 over 5 plus 1 over 6. And when we sum those three, then we do 1 over that sum. And the purpose of that is, like, so the example I was given earlier is if you're doing the average speed, for example, where you have a larger speed, right, you're also covering distances faster, right? So you want to, it's like trying to weight things such that the larger number is not skewing it because of the nature of what you're averaging. So there are different use cases. Like, there's a speed case, there's PE ratios. There are specific cases where you would use the harmonic mean, like the ones I mentioned. But essentially, what you're doing is you're taking each observation, you're doing the inverse, you're taking a sum, and then you're doing the inverse of that sum. Now, for the weighted mean, think about it this way. For the weighted mean, you're trying to find the mean of a certain variable, but each data point for which you're trying to get a mean have different importance. And the example I gave was, for example, imagine you have, in a bank, you have 2 credit cards. One is they charge customers 10%, the other card they charge customers 20%, right? If you're asked what's the average interest rate charged to customers, you're not going to do 10 plus 20 divided by 2 is 15%. And the reason being, what is the thing you're charging interest rates on? For example, is outstanding balances, right? So let's say in the 10% case, you had $1,000 outstanding balance. And in the 20% case, you don't have also 1,000, but you have 5,000. So that means you have 5 times more balances in the 20% bucket. So obviously your mean is going to be skewed more towards 20. It's not going to be 15. It's going to be a number much closer to 20, like 18.5 or 19. So what you're doing in the weighted mean case is you're saying 10% times the weight, 1,000, plus 20% times the weight, 5,000. And then you're dividing by what? 5,000 and 1,000. So divided by the weights, right? And when you do that, you're going to get a mean that gives you a mean that's skewed towards the weight of importance of the two individual numbers, which is just the two cards in your portfolio, if that makes sense. Maybe I could illustrate this with numbers, but I just need you to understand this conceptually because we're just like revisiting stuff we've done before. Someone else's hand was up. I think UG.
Oh, sorry, it's the same person. I just dropped it. It's
okay.
better.
Okay, nice. So just think about it this way. You're just multiplying the weights, and then when you're dividing, you're dividing by 1 over n as well. So in each case, you're multiplying the weights. Same thing, if you remember like your frequency table, it's the same thing you're doing, right? If you have a distribution of numbers 1 to 10, and then they give you the frequency for each. 1, there's 20, 2, there's 50 of them. So you're just multiplying each by the weight, and then you're dividing by the total frequency. So it's the same idea. And in Excel, you just do some product of, the two ranges, so weights and the numbers, and divide by sum of the weights. Yeah, so I hope that helps. So another measure of center that we look at is the median. Does everyone remember what the median is? Please let's get thumbs up for people that don't remember, and you can drop a comment like, "Oh, I've forgotten." Yeah, just to keep things interactive, but I'll still explain anyway. So the median, remember now, we're saying with your data, when you're doing descriptive statistic, one very common thing is the mean, so your average. The next thing is you have a distribution of data, right? What's the middle point? Remember, with measures of center, you're trying to get one statistic that represents the middle point or the central value of that sample, right? So the median is just the middle, right? When you order values of observations from the smallest to the largest, or the largest to the smallest. So when your numbers are ordered in a certain sequence, the middle number. So if it's an odd number, your number is just the middle, n plus 1 divided by 2. This is all jargon, like don't get confused with it. If you have 5 numbers, 2, 2, 4, 7, and 8, there are 5 numbers, so your third number will be the middle number. And 3 is just what? 5 plus 1 divided by 2. So that's just to help you get what number, what position is the median. So if you order your set of numbers, if there are 5 numbers, the third number is going to be your median when the numbers are ordered, right? So, and that third is just, you always do n plus 1 divided by 2, right? When it's an odd number. So if you had 7, the same thing, your fourth number will be the middle. So 7 plus 1 divided by 2. It's just a short way to always know like what number to go to get your median. And for even numbers, like when you order it, you pick the 2 in the middle. So if we had 6 numbers, the first, the second, the third, the fourth, the middle will be the third and the fourth. So you just do the average of the 2 numbers in the middle. So that's what it says here, like x n over 2 plus x n over 2 plus 1. So the n over second over 2th entry plus the n over 2 plus 1th entry, and then we're getting the average of those two. So once again, if you had 4 numbers, 1, 6, 8, and 9, 6 and 8 are in the middle. So on the left hand, you have 1, on the right hand, you have 9. So 6 and 8, the average of both would give you 7. So that's the median, right? So I hope that makes sense. It's straightforward enough. And to get the median in Excel, you're just saying equals to median. Now, so that's for median. So for quartiles, this is a typo. Oops. Right. So for quartiles are just it's the same concept, right? So your median is dividing your distribution into 2. And if you divide each half of that division into 2, then you have quartiles. From the word quart is just 1/4, right? Quarter. So if you take the 25th percentile, you have to, so let's use this diagram on the bottom. You can see the green diagram. So where you have Q2, that's your median, right? So if this was a distribution of numbers, in an ordered manner, remember it has to be ordered. So from minimum to maximum, the middle mark is Q2, which is your second quartile. Now that divides the distribution into 2, right? So one half and the other half. Now, the midpoint of the left half is Q1, which is your first quartile, right? So you have quarter on the left, quarter on the right, middle, quarter on the left of Q3, and quarter on the right of Q3. So this is your first quartile and third quartile. I think that's pretty straightforward. Does anyone have any question? Just raise your hands, or you can just drop a comment as well, and I'll just repeat and explain again. Right. So we're good, right? So same way you can slice your distribution. So just think about it this way. You have numbers, whatever it is, sales, age, number of purchases, whatever, the business data is. If you want to have a sense of how the data is distributed, where the midpoint is. So if, for example, we had ages of students in a class, and you had your youngest student was 10 years old and your oldest student in that same class was, let's say, 16, right? So you just want to have a sense and remember, what you're looking at is all the ages lined up. Like if the lowest age is 10 and the largest is 16, your midpoint is not dividing. This is not arithmetic mean. You're looking at the midpoint. So if it's for 10 students, you have to list the 10 numbers, right? And for 10, the average of the 5th and the 6th number will be your median, whatever that number is. Okay, so I wanted to explain quartile again. Yeah, I will. So let me see. Maybe I should just drag Excel into the screen. We can take some examples. Let's say we had, in that class I was mentioning, we had 10 years, 11, another 11-year-old. Remember, it has to be in order, right? And 14, 16, 15, another 15-year-old, another 15-year-old, and a 16-year-old, right? So here we have 9 students, right? So remember, it's an odd number. So the middle of 9 students will be what? The 5th student. So the 5th student gives us 4 students on one hand and 4 students on the other, right? So in this ordered data, this is your median. That's the whole point. So your median splits your data when ordered in the middle. So if I say we have a class where the younger student is 10 and the older student is 16, or you have sales numbers, 10 purchases and 16 purchases are the max and mean that a customer does. Like, don't do 10 plus 16 divided by 2. 13 is not the median, right? So the median is dependent on the distribution of the data, right? So in this case, our median is larger than the mean, right? Okay, so what I was saying with the quartiles was if we split on the other hand into 2 again, so right, if this was the new distribution on the left and this was the distribution on the right, So the quartile here will just be splitting this into 2 again. So it will be 11 plus 11 divided by 2. So here we have 4 numbers, so they're even, right? So in the same way, you would split it that way. So 11 here, and in this case, 15 as well. So the quartiles just divides the distribution into 4 parts, such that you have a quarter of the frequencies of the data in each group. So I'll take this away now. So look at this diagram again. So if there's a number line and you have your numbers ordered from min to max, the median is the middle point, the middle number, not the middle point, like dividing, saying sum of minimum plus maximum divided by 2, but based on the frequency of the number. So remember what I did here, like we're listing the actual numbers and the number in the middle based on the position. Right? Think of middle as position within the data. And yeah, that's minimum, maximum, median, first quartile, second quartile. And this idea can be extended, right, to have deciles or percentiles. So you remember, like on many standardized tests, you hear like percentile, 98 percentile. So 98 percentile just means like your score is higher than 98% of the distribution. So you're in the top 2%, right? So you can slice this into as many parts. Some, like you see deciles a lot, especially in marketing, like in RFM, frequency recency modeling. Like there's this thing where like you want to send your email targeting to the top 3 deciles, right? For example, so it's very typical to split into 10. But you're not just dividing it even into 10, like it's based on the distribution. So that number is not like taking min plus max and dividing it into 10 parts. Is laying out the distribution of the data. And if you have 100 customers, there will be 10 customers in each decile. So that's it. Yes, the data must be ordered to find the median. Yeah, that's a good point. So ordered data. So minimum to maximum or maximum to minimum. The order doesn't matter, but it has to be ordered, whether it's big to small or small to big. Yep. The other thing that's important is mode. We know mode is just the highest occurring data value or interval. So interval is where you like bin the data. So if you had like age in the population, right? Many times if you have from 0 to 100 years, right, in your population, you may not have to build your distribution using each age. You could say ages 0 to 10, 11 to 20, 21 to 30, like that. So that's why you say or interval. And the mode is just the highest occurring data value or interval. So in Africa, for example, many countries that have a young population, like what you're going to see is you see the bin that has the highest mode would just be the bin that has the most number of individuals, right? So mode is just the highest occurring data value. So if you had 224466777, I said 7 3 times, so 7 is the mode. So just the data point with the highest frequency. And this is how you do it in Excel. Now, in Excel, you have mode single and mode multi. Nothing special there, but just in some cases, and we'll see that like as we go on, you could have a distribution that has more than one mode. Also, ultimately, there could be a number that has the highest mode, right, which is fine. But in some cases, you could have 2 important modes, like a camelback, right? So you have high frequency here and high frequency in another value, and you could find more than one mode in Excel. Essentially, I'll explain some more of that as we go along. Yeah. So remember, I said I'll be focusing on the application of what we're saying. So the mode is usually very important or very useful when you're doing descriptive statistics of categorical variables. Remember when we looked at data types, right? Where there was categorical, there was numerical, right? Quantitative data and qualitative data or categorical. So if, for example, to the point I made last class, if you're saying color preferences of kids in a kindergarten class, right? You cannot find the median color, right? Because of the nature of data, it's just categorical. So then the mode could be important. So what's the mode color? So what color has the highest frequency? So what color do most number of students have as their best color? So you see, in terms of representing your data, mode is a useful statistic when you're dealing with categorical data. Hope that makes sense. Right. So if you're modeling, you're presenting data that has, for example, customer preference, right? You have 4 kind of pot SKUs that we just launched for a particular brand, and you want to show like how people are buying. For example, you're going to say, this is the product people are buying most, and this mode they're buying, the mode is 2 times higher than the next frequency of purchase. So you're quantifying preference, which is like pot selection, but you're putting in a numerical form that makes sense that you can quantify it. So mode is very useful for categorical variables. Frequency tables. So nothing too special here. The frequency charts are just very useful descriptive representations, right, for categorical variables. So once again, it's the same idea I just explained with modes. So if you had, for example, different kind of chocolates and you want to see, you want to show that data, you have the frequency, the number of times people purchased, or number of students that like that kind of chocolate preferences in a class, right? So dark chocolate, 37% of the time, milk chocolate, 28% of the class, so 29% liked it, and so on and so forth. So this is a graphical way to show, categorical data preference. And when you have more than one variable, you can also do what you call a cross-tab analysis. So it's just cross-table analysis. So what that does is just, so for example, if this chocolate preference was for the whole class, you can layer on top of it like ladies or male and female students, right? So it might be that the female students liked caramel much more than the male students. So even though caramel came third here, caramel might be the highest frequency among ladies. So you already can start seeing how this becomes useful. So let's say you're analyzing sales in a store and you want to look at your sales or preference of a particular product line given different demographics, right, within the store. So it may not be enough to just say, let's see the frequency table or frequency graph for the different kinds of chocolate. You may want to say, let's slice that by gender, or let's slice that by age, or let's slice that by customers that have a loyalty product or don't have a loyalty product, right? So you start seeing how to think about the data you're seeing and to try to get insights out of it, right? So here, this is just an example where you have feedback from customers, right? Unsatisfied, unsure, satisfied, right? So this is like ordinal, but categorical data, right? And then you have gender, so males and females. So for the males, you had 25 unsatisfied, 12 men were unsure, 50 men were satisfied, right? So for the ladies, you can see here, for the females, you already have a much lower percentage of unsatisfied customers. Now, if you lumped this together, right, all you would see is 30 people were unsatisfied, 32 were unsure, so about the same number, and 86 were satisfied. So you could come to the wrong conclusion just looking at the total. You could say, we have about twice as much people, a little over twice as much people are satisfied than are unsatisfied, but that's not the case. It's the case with the whole population, but among the females, lots of females were satisfied. So somehow, let's say this was for some product, the product is doing well with the female population of the store, for example, right? And you can only get that insight by doing a crosstab where you're splitting your frequency for your categorical variable along more than one variable. So when you split it by gender, then you can see some more insight. So only 5 out of 36, right? Which is less than 17% are unsatisfied in the female category. So the product may be meeting female needs better than male needs, let's say. So just to explain, like in practice, how these ideas like are useful, not just like this is how to punch this, and this is the formula for this. Okay, let's go on. So far, is there any question? Like, does it all make sense to everyone? And are we able to like tie business reasoning to it? Let me pause and get some feedback. Any other question? Anything in the chat? Someone wants to raise their hand and say something? Now is a good time. Okay, none. Let's go on. Okay, makes sense. Thanks. Because let's keep it a bit interactive so I know like we're all in this together, we're following. Now, so let's talk about distributions a bit. So remember the comment I made earlier, like when you look at the mean of a set of numbers, like it tells you something, but it doesn't tell you everything. It doesn't give you a holistic picture. You just say, okay, that's the middle. As far as we're concerned, that middle could be due to one large number or one very small number that might skew the mean in a certain direction. But distributions help show the shape of the data for a given variable, right? They help you understand like how each variable's data is distributed. And usually we use frequency distributions to show this. And the frequency distribution, remember, is just telling you the number of times a particular number is occurring, or a particular data point is occurring, right? So just follow me, like look at the top left corner in these 4 graphs. So you can see, let's say each stroke is a number under. You can see 7 to 13. So you have very few numbers are around 7, and then the strokes get a whole lot around, between 9 and 11, and then it gets lighter. So what this is just illustrating is, now look at the big like bell-like shape here. Oh, sorry. So what this shape is just showing you is, so this on the y-axis, on the vertical axis, is the frequency, right? Or relative frequency. Many times you just use relative frequency, but anyway, think about y as frequency, right? So the higher this number is, the higher the frequency. So you have your highest frequency at about 10, right? And what number is that? The number with the highest frequency, that'll be your mode, right? Now, your mean is just the average of all of these numbers. So if each black line is a number, the average of each individual entry, the arithmetic mean of each individual entry is the mean. So you see where the mean is located. The mean is the diamond shape there. The median is the middle point. So wherever the median is, what that means is you have the same number of entries or data points on the left-hand side and the same number of data points on the right-hand side. Now, is this clear enough? Like, just give me some thumbs up, or I just need everyone to understand this, because all of our discussion will be around understanding this. So once again, each stroke is each data point. On the y-axis, you have the frequencies. So if you have lots of numbers are between 9 and 11, that's why you see the curve is high in between 9 and 11, so the frequency curve. Where it's the highest frequency is the mode. The mean, arithmetic mean, is just the sum of each of these numbers divided by the number of numbers there are, just arithmetic mean. And the median is the middle point, such that on the left-hand side, you have the same number of entries as on the right-hand side. So now, what you have on the top left corner is symmetric data. So you see how the data is very well centered around the mean. So the mean and the median are about the same number. So what this means is that on the right-hand side of your mean and on your left-hand side, you have about the same amount of data distributed, and the distance from the middle number, the arithmetic mean, is about the same. So you see, this is very symmetrical. And on the right-hand side, you have skewed data. So what skewed data just means is, now look at the numbers at the bottom. You have between 0 and, let's say, 7, right? Now you have lots of your data lies closer to the 0 mark, so about 1. And then as you go further from 1, it's just like few numbers. So let's say let's look for a real life scenario that could be this, right? So let's say we had a class, right? A kindergarten class, let's say, or a nursery, a preschool class, right? Now, most of the students are just coming, they're like 1 year. Some people bring their children really early, like less than one, but most people come between 1 and 2, and they're just playing, right? So they're all in the same class. But then there's some, let's say, it's not the most pleasant example, but let's say some kids are a bit slow or are having learning challenges, and they're much older, but they cannot go to another class because they're, let's say they brought speech therapists, they're bringing people to try to help them, right? So there are a few students that are much older, but shouldn't be in this class, but they're here, right? So you can see the distribution. So this distribution is skewed. So you have most of the data lies here. Of course, there's nothing below 0, right? Because you cannot have kids that are less than, like, below 0 is like they're not born yet. And it's more sparse as you go up because there are fewer kids on this higher spectrum that are old but in preschool, but most of the kids are around here. So this is just to help you picture like what these distributions mean as we show them and discuss them. Now look at where the median is. So the median is right here. The median is like under the bell because you have very many students less than, let's say this middle mark was 1, or like, anyway, let's say 1, right? So you have lots of students less than 1 and lots of students above 1, but then the distribution above 1 is a bit bigger, right? It's like a wider range. However, the mean is here. And why is the mean on the right-hand side of the median? It's because you have some bigger numbers. Remember, your mean is, your arithmetic mean is you're summing all the numbers or all the data and dividing by the number of data points there is, right? So these big numbers, these outliers, are pulling the mean away from the median. And this is what you call a distribution that's skewed right. So remember, when you're saying skewed left or skewed right, just look at where the bell hump is and then like call the opposite. So here where the hump is on the left, this is right skew. And in a distribution that is skewed right, the mean will be greater than the median. Right, hope that makes sense. And that's the case because you have these outliers that are much bigger and are pulling the mean in that direction. So imagine if there was a 100-year-old person that chose to enroll, that's ridiculous, but chose to enroll in this class, right? Then this mean will be skewed far away because that 100 would be added to the sum, and yet it accounts for just 1 data point. So 1 in the numerator, 100 in the 1 in the denominator, 100 in the numerator, right? So you can understand why this mean is skewing in this direction. Now, all this explanation to say, when you see your data sample and you look at the distribution and you see that the mean is larger than the median, you can already start thinking that this might be skewed right. So this is skewed data, right? Look at this example at the bottom left corner. This is bimodal data. You remember where I was explaining that you could have multiple modes, mode multi in Excel, this formula. Now, there are cases where you have multiple modes, right? So 2 is just like the data is concentrated around 2 high frequency numbers. So it's concentrated around 0 in this case and around about 6. So this is just bimodal. So 2 peaks with the 2 clear, distinct peaks on the frequency axis. This is skewed data. So, data with outliers. So where you have a few extraneous points within your data. So you can see most numbers here around 10, but you have some really extraneous numbers that are far away. So again, with the same thinking I explained earlier, all this does is this outliers are pulling the mean far away from the median, right? So not all of this is not just like present statistics and mathematical stuff, is to explain to you, like in practice, what do these mean, right? So if you're analyzing data, right, you're showing the mean of customers. Remember what I was saying about if most of your customers spend $1,000 and then there's this one customer that spends 1 million, you can see that your mean is not going to have so much meaning, right? Because it's pulled away from the bulk of the data points, the main distribution by that outlier. So there are different ways you want to deal with outliers. Do you want to treat these kind of customers separately? Do you want to do a segmentation split where you look at high spending customers, low spending customers, and you can look at the low spending customers and look at their own average, look at different variables that pertain to them and make the business decisions that improve the outcomes of those guys, and treat the high spending customers differently, as opposed to just having the one number, which is totally not under the distribution of the main customer number, bulk of the customers you're concerned with, right? So these are the kind of things I want us to begin to think about as, seasoned data analysts. Same thing with this bimodal data. Do we want to split the data, like segment it, as opposed to using a mean here that may not be as meaningful? Right. So just on the right-hand side, not to dwell too long here anymore, is just showing differences in mean and median, and the mode show very useful information. I've explained that, we've discussed it. And this is just a short schema that just shows you right off the envelope how to think about skewed left, skewed right symmetric data. So with symmetric data, the mean, mode, and median are at the same point. With skewed left, you have the mode higher than the median, higher than the mean. So remember this case where it's skewed right, you have the mean is higher than the median, larger than the median, and that's what you see here. And that's just because like lots of the numbers on this side pull the mean away from the median value. Does this make sense? Yeah. And some real life examples like height in the general population, right? Human blood pressure, right? Does anyone want to take a shot at how would human blood pressure be skewed? Would it be right or left? It depends, right? First, it depends on, how many people are hypertensive, and then there would be like this harsh cutoff because most people will be around the same, and then some people will be really high, right? At some point below, if you're too low, the distribution cuts, you're going to die, and if you're too high, you'd have a stroke and die. So each time you're thinking about data that you're working with, always think about it in terms of like, what's the distribution of this data? What makes sense in terms of the distribution? And that helps you to start looking out for outliers and seeing what fits and what doesn't. Okay, yeah, let's pause here and do some practice. Let's do this together. So I'm going to need responses for each case. So let's be ready. So the first is just talking about data and variable types. So state which type of data type each of the below represents, and then which center measure can be used for the variable. So remember, what I want you to think about is this. Remember this chart where we have qualitative or categorical data, quantitative, ordinal, nominal, continuous, discrete. So let's go. Answers in the chat. So a collection of data on people's likelihood to vote for a candidate: very likely, likely, neutral, unlikely, very unlikely. What data type would that be? Let's go. Answers in the chat, or you can raise your hand and just unmute yourself and answer. Hello? Any takers? We're really quiet today. What's going on? Does anyone want to try in the comments? So great. Someone said categorical, right? Good answer. So categorical, is it Is it categorical, ordinal, or nominal? Qualitative, great, same. So now the next question is it ordinal? Is there a certain order in it, or is it nominal?
I
No,
would say nominal.
Okay, good try. Someone said ordered as well. So depending on how we view it, in this case, we could view it as ordinal because you have very likely to likely. If we're going in the direction of getting a vote to a particular candidate, we can say we're moving from very unlikely all the way to very likely. So there's a certain order. But also it's neither here nor there, depending on if we're looking for neutrality, like if we're testing number of people that are confused, right? So unlikely is the midpoint in that case. But anyway, it should be ordinal because a certain sense of direction or order within it. It's like first, second, third, likely, less likely, very likely, and so on. The next is you collect data on the diameter at breast height of trees in a forest. What kind of data would that be? Diameter of trees, quantitative, great. So is it discrete or continuous? Everyone has the slides, right? Remember this breakdown. So is it discrete or is it continuous?
That should be continuous.
Exactly. Thank you. So continuous for things like length. So we can subdivide it indefinitely. So you collect data on the year wineries were started. What kind of data would that be? Year, someone said ordinal. Yeah, so years, like this one of those that is a bit tricky, like years, yes, will be categorical and ordinal because like in what year did it start? Some people choose, if you're using date or time as time, like as periods, then it could be divided and it could be viewed as quantitative or numerical. So it depends. But usually, if you're saying the year in which wineries were started, like we could say it's ordinal. But date is one of those that jumps around a bit. If you're looking at difference in time from the dates, then you could say it's quantitative, or it could be categorical, depending on how you're viewing it. So the next is you collect drink types that people in Sydney, Australia drink. Yeah, correct. Drink types were here. Nominal. It's no sense of order and it's qualitative. You collect height of plants, so we've done something similar, so that's quantitative, continuous. You collect data on cars that people drive. So what car? Once again, that's nominal. You collect data on temperature at different locations in Antarctica. So what's temperature? Temperature data. Great, continuous. And you collect data on the first, second, and third winner in the beer competition. Last one was that. Ordinal, great, because of the order of the categorical variables. So great, we're following. So center measures. So here, what's the median, first quartile, second quartile, minimum and maximum of this distribution? Sorry, this keeps happening. So let's drop numbers in the chat or unmute and speak. Normally, I enjoy when people actually speak more, but up to you guys. But so what's the median? 13, good. What's the second quartile? Any takers? Second quartile. Come on, anyone can try. Like Let's not stay long on this. What's the second quartile? Okay, what's the first quartile? You can drop in the chat or unmute and share. Someone said 10, good. Any other answers? Come on, guys, answers in the chat. Like, just put one number you're thinking, like, doesn't have to be, it may not be correct, but just so we have options to discuss. I know 8, okay, 9. Okay, so remember the Q1 is this point. So if your data is split into the 4 parts based on frequency, right? So this is the minimum, this is your first quartile. The second quartile is the same as the median. The third quartile is just like the right-hand side of your median split into 2 again, right? So in this case, the minimum is 6, first quartile 8, median 13, second quartile 15, and max 20. Now, in most symmetrical distributions, if you remember from here where we saw, right, that interquartile range, remember from high school, secondary school, maybe primary school for some people, this interquartile range is just your second, third quartile minus your first quartile, and that's your interquartile range. So that would just give you a sense of the spread of where the bulk of the data lies. First quartile is 8, the start of the bar. 9 is somewhere here in the middle. So this is usually called a box plot. So in statistics and in looking at data a lot, you come across this a lot of times, a box plot. So the box plot just shows you at a glance the range of the data. Remember, range is the minimum, the maximum minus the minimum, right? So this is your range of the data. The range of this data is 14, so 20 minus 6. The interquartile range is the third quartile minus the first quartile, and that's what? 15 less 8. So that 7 gives you the range of where the bulk of the data lies. And if you're looking at a symmetrical distribution, as in this case, your interquartile range is going to be somewhere within here, right? And then you're going to have your 25%, 25% here, 25% here, but the bulk 50% centered around the mean and the median are going to be that within that your interquartile range. So that's why we use box plots a lot. So this box plot, and these are the whiskers. So like with cats, you call these lines here the whiskers. So is everyone good? Let's look at the last example. So this is, so you have a distribution, a couple of distributions. You have this graph. So each box plot, think about it as a distribution, right? So this is a distribution that has minimum 6, maximum 20, and the median is 13. Now, so here we have cyclists, you have their age, you have means of transportation on the road, right? And you have the age. And you have cyclists, you have drivers, passengers, and pedestrians, right? And these are like box plots for each of those distributions. So this is just the age distribution of cyclists, the age distribution of drivers, age distribution of passengers, and age distribution of pedestrians. All right, so the question is, which row has the most skewed distribution? Now, remember what a skewness shows you. When you have like the bulk of data on one hand and lots of outliers, you have that skewness. So it has to do with the shape of the distribution. And we've talked about that. So anyone wants to try, you can drop in the chat which distribution is most skewed. Someone said cyclist. Any other option? Someone said passenger. Okay. Passenger. Okay. Many people are saying passenger, and that's correct because you can see this passenger, the bulk of the data is here. Look at your interquartile range here, right? Look at your median and look at all these outliers. You can see the whisker on one hand is really large. right, with many points. This like shows you like that skewness of the distribution. Another thing to look at is just in terms of the width. So look at between, remember, this is your first quartile. So that means all here up to this point is 25% of the data. You have within this short interval of age, you have another 25% of the data. You have 25% of the data here and then 25. So you can already see that the data is really skewed. As you can see, as the distance between from the median to the third quartile versus from the first quartile to the median. So I hope that's clear. Now it says 50% of cyclists, so now we're in this distribution, 50% of cyclists involved in accidents were above what age? Will someone attempt that? 50% of cyclists involved in accidents were above what age? Excellent, above 25. Yeah, the number is somewhere between 20 to 30. Like I as far as I understand, like, you know, the concept here is like 24, 23. But yeah, so the median line cuts the distribution into two. So you have 50% on the one hand, 50% on the other hand. So that means we're following. And if anyone has a question, this is a good time to ask. So what percentage of pedestrians involved in accidents are below 21 years? What percentage of pedestrians involved in accidents are below 21 years? Let's get a quick response. Someone said 25%, 50%. So what line should you be looking at? Just remember we have more 50%. Yeah, that's the correct answer. So remember 21 years is here. If you trace that to the distribution for pedestrians. Oh, what percentage is below 20? Oh, sorry. I was looking at passengers. The 25% people are correct. My bad. So I was looking at passenger, but like this is pedestrians. So it's the same idea, right? Below 21 years, so you trace 21, not to passenger, but to pedestrians, and it coincides with this. And this line, remember, is the first quartile. So you have 25% here. Between here and here, you have 25%. Between here and here, you have 25%, and above this, you have 25%. So sorry, the 25% people are correct. I feel like many people made the same mistake I made. Like, we understand the concept, but we just mixed up passenger and pedestrian. Anyway, so just to wrap up this portion, you see how distributions work, right? So these are already like insightful comments, right? We have 50% of cyclists involved in accidents are above 24 years, right? We have 25% of pedestrians involved in accidents are below 21 years. So these are now like value statements, judgment statements that make sense, that already start helping to shape, create a story, a narrative, and you're inferring all of that from the data. So this is how I want us to think about using all these measures of center, descriptive statistics. Always think about it like, what does this really mean? If I have data, if I have a distribution, like what do these statistics mean? Like median, mean, mode, interquartile range, quartiles. What ways can I present a story? Can I get insights from the data? What's the data telling me using these different tools? So it's never just about punching numbers and knowing the formula for things. It has to be about being able to craft the message that comes out of the data, right? If this was sales data, for example, it could be 25% of people purchasing are purchasing below, like their checkout basket at Walmart is below $80. Okay, like, so we're saying, okay, we have a large chunk of people, a small chunk of people that have a small basket. Like, you always have to think about the story in terms of narrative, and statistics help you like paint that picture. Right, so now we'll have another example, and I'm taking some time to really explain these foundational things because these are the things that help you when you're doing like your analysis. I will talk about tools from next week. We'll be doing a lot of like tools things, but I need the foundation to be right. Okay, so let's look at these distributions, right? You can see the different shapes. And please, if people can unmute and answer or attempt these questions, it would be really cool, right? So 1, 2, 3, 4, and we'll just drag each of the scenarios to the number that matches it. So a uniform distribution, a distribution that's skewed right, a bimodal distribution, remember this, and a distribution that's skewed left. So the first case, the first data set is university entrance exam scores for medicine students and mass communication students in Nigeria. So what number should this move to? Escape. Sorry. Someone said 3. Okay, everyone's saying 3, right? Okay, so you have 2 courses, and for those that schooled in Nigeria, we know what we know how this fits, right? Which course has is on the higher end of the bimodal distribution? We can tell, right? We can infer that. So let me try and drag this actually. Well, right. So this comes here to 1, all right? So 10,000 house prices within a given geographical area. What distribution does this go to? Maybe we should go to the other ones as well. The last one is men's clothing sizes for 10,000 adults. Where do we think this should go? Clothing size for, let's say, pants. Someone said 4, okay. 4, I'm seeing a lot of 4. Let's try and give like 5 people responding at least before I put something somewhere. So more people. I see answers from Ife, from Ayi. Come on, guys, where should this go? What kind of distribution would the data for this fall under? Are we there? There's some more answers. Some are saying 2, Cynthia saying 2, Nelly, Francis saying 2, Nelly saying 4. Where's Aisha? Where's Akiomi? Where's Babs? Where's Juliet? Candy? It's a large class, but most of the class, you guys are not participating. Okay, I'm getting more answers. So it's left skewed, but not sure if it's to the left or right. So this is where we have to always think about the data. So remember, it's men's clothing. Now, in terms of the size distribution, what I would think would be there'll be a cutoff below which that size will be in the kids section. So we can say we expect the smallest man to be a certain size, and so there'll be a cutoff on the lower end. So I would say 2. Do you get my reasoning? Like, if you had this distribution, let's say this is from size 4 to, you may go to very, very large people, but below a certain number is not men's clothing anymore, right? It's like kids' clothing. Cholesterol levels of adults, where should this go? Normally, I like to get answers with the reasoning behind them. So let someone try for the cholesterol. Someone said 3. Okay. 4. Okay, I'm seeing 4. I'm seeing 3. People are saying 4. Can anybody say why? Yeah, Ronan, please go ahead.
No, sorry, I actually have a question regarding the one you placed against 2, which is men's clothing size for 10,000 adults.
Yeah.
And I'm curious why it is 2, because wouldn't there be other factors that may have influenced, that size? For example, if you're picking the 10,000 persons or the 10,000 men from, say, Nigeria versus 10,000 men from North America, I'm imagining, the geographical location as well could impact on on those sizes. So
yeah,
why could it be skewed to the left and not evenly distributed between the population size or the sample?
That's a great question. And definitely there'll be lots of factors that affect, like, geographical region, like what country. Some countries, are more obese than others and whatnot. But my reasoning for putting it there is actually the cutoff of the distribution. So I'm imagining the left-hand cutoff to be the minimum size for a man's pants. Like, it cannot go to 0, right? It cannot keep going low because there's no, let's say the size is from 4 and it keeps going on and on. Like, at the very extreme large size, you're going to have very few people. Because let's say, like, people here are extremely obese. You have lots of people that are like really, really big. But as far as his men clothing, at some point there's like a cutoff. Beyond that is like kids section, right? So it's this cutoff that's informing putting this against 2. But yeah, you're right that, the distribution shape would depend on different factors, but just, that cutoff is what informed putting it here. So let's say this is the minimum smallest size, like for the men's section. Let's say it's like, if it's waist size in inches, let's say starting from size, 22 or 20. Below that, at some point, like, it's just children's, no more men's clothes. But then on the larger end, you can probably go to people that are like really, really, really big and, goes all the way. Or people that have like real extreme obesity. So that was the reasoning.
All right, thank you.
No problem. And then someone else said for cholesterol 3, someone changed to 4. Can someone that put 4 just, talk about why they're thinking 4? Part of this exercise is just to help us discuss the data. Yeah, let's go. I heard your voice, please.
I'm thinking 4 and for the cholesterol level, because after a while there'll be deaths, and that's blockage, that's stoppage. After a while there'll be deaths if there's cholesterol. So I'm thinking 4, so that it will skew to the left.
Absolutely, I agree. So above a certain point, we can assume the cholesterol kills the patients. So. But then some people have like really low cholesterol, either dietary reasons or medical reasons. And for the house prices, we can put in 1, can be, fairly even distribution, because within a particular geographical area, what you see many times is, the housing price is like this amount. Some people are selling lower, some are selling higher, but most people are around a certain average price, right? Depending on how the market moves, most people won't sell around a particular number. So yeah, so I hope like with this section, like we're able to just also train ourselves to think about the data. Really, really important. Some analysts just rush past this point and just rush into, you want the formula, you want to start writing SQL, but you need to learn how to think about data, how to always think about the real life implication of whatever data set you have. And that's what will make you stand out as an excellent data analytics practitioner as opposed to some other persons. Ultimately, many of these tools and techniques, like there's lots of support to learn them. There's like videos, there's ChatGPT that helps with a bunch of stuff as well. But ultimately, you need to know, like, for when you're looking at statistics, what does it mean? Like, how do you use it? Like, how is this valuable? And that's why, like, in going through all the different things I teach, I try to give you that, kind of business school approach to how am I going to use this? Like mode or median, like why does that matter, right? And hence these examples we're going through. So let's go on. So now we've seen measures of center. Remember I said, like, when you have the mean, or maybe we should take our short break. Like, we'll just take a quick 3-minute break. It's 9:17 now. We'll reconvene at 9:20. So in 3 minutes. Let's just take a small break so, people can get water or stretch their legs. We'll be back in 3 minutes. Jamaica, you can stop recording. Okay, so now that we've looked at measures of center, and the measures of center were like positioning the data in the middle, like a statistic that shows you like the central point or central tendency of the data. The next thing will be measures of dispersion or variability. And this is really important because they give you a sense of how the data is distributed around the center of the data, right? So they portray the amount of dispersion within the data. And you have a couple of them. Like we've already looked at the percentiles and quartiles and mean. So one very obvious measure of variability or dispersion will be the interquartile range. And we talked about that. It's just your Q3 minus Q1. So your third quartile minus your first quartile. And if you have like a symmetric distribution, come on. If we have, let me go back to presentation mode. Okay, so if we have a symmetrical distribution like this, where the mean, and the median are in the middle, you have 25% of the data here on the left and right, you have another 25% here and here, right? So your interquartile range would just be the difference between this point, and it gives you a sense of how spread the data is. Remember when we looked at this example where we weren't using a frequency curve, but we're using like box plots, we asked which is most skewed or which is wider. Like you can see a spread in the data. You have much more skewness here, but even in terms of spread, you have widespread in pedestrians as well. So just think about it in that sense, like where the majority of the data lies within the distribution of the data, right? One very well-used measure of variability will be, a couple of them will be absolute deviation, variance, standard deviation, right? So the absolute deviation is just what? The difference from the mean of each data point. So you remember when we looked at what the mean was, I said the sum of deviations around the arithmetic mean will be 0. So if the mean here is 2 and your data point here, remember we're looking at all the y-axis values. So if the mean is 2, this data point where y is 1 is minus 1 because it's 1 less. This one above is 4, so that's 2. So that's the distance, right? And the sum of all these will be 0. Now, the negative ones are canceling out the positive ones, obviously. So the sum of deviations is 0. Now, the metric I just mentioned now is the absolute deviation. So the absolute value of those deviations around the mean. So in the case where you had the distance from the mean as -1, that's just going to be 1. The one above is still 2. The next number that had -2 is going to be 2. So you're just taking the absolute value of the deviation relative to the mean of each data point, and then you're getting the average of that. Now, what this tells you is, once again, looking back at that picture, what this shows you is it tells you how much these points are scattered away from the green line. So the green line is the mean. If points are really scattered far away, your absolute deviation is going to be 2 plus 1 plus 1 plus 0.5 plus 0.5 plus 0.5 plus 1.5 plus 1 plus 1 plus 1.5. Now, here you're not saying minus 1.5, even though it's negative, but taking the absolute value of each. So if that number is really large, then you know these points are really far away from the green line. And then when you have all those numbers summed, you're just taking the average based on the number of points. And you have to count the zeros as well, right? So this will be 1 plus 0 plus 2 plus 1 and so on. And then you sum all that and divide it by the number of points there are. So that gives you a sense of scatter, a sense of dispersion of the data. Right, so let's get back here. The next thing we look at is the variance. So the variance is just the average squared deviation. So one way to get rid of the negative numbers, so the numbers that are below the mean, is to use the absolute value. Another way is to square them, because we know a negative number times a negative number is positive, right? So another more useful way is to use the variance. So the variance is just squaring each deviation, like each data point's deviation from the mean. So xi is each unique number. Egg bar x is the mean, arithmetic mean. And so that difference, we're squaring it and taking the average of those squares. So if we go back, so in this case, it will be -1 squared, which would be 1, 0, 0, 2 squared, 4, -1 squared, again 1, and then you're adding all those and then dividing by the number of data points. So really straightforward, and that gives you the variance. And the square root of the variance is the standard deviation. And in Excel, how you would show these is just standard stdev s and var s to give you the standard deviation and the variance, right? So look at this distribution here. Remember, the variance, the absolute deviation, the standard deviation are giving you a sense of the dispersion of the data, how wide your distribution will be, how dispersed it is, right? So look at sample A, the blue line, B green, C yellow. What sample has the largest standard deviation, the largest variance or standard deviation? Just a quick answer in the chat. It should be just quite obvious from the picture and what we've said so far. Let's just get an answer 2. Okay, someone said A. So yeah, A is the number, blue. And you can see that, like you can see how widely spread, how dispersed the data is. Now, so think about it this way. Remember I was saying, like when you're looking at the data, you're analyzing it or you're getting insights from the data, these 3 distributions have the same mean. So the mean of, let's say this was sales, this is sales in 3 different stores. They all have 200 as their mean. But that's not the whole story about the data, right? For some people, you have, a fair number of people as like purchasing very small. A fair number of people are also a bit big, and the middle is 200. For some, you have most people are doing like 200. Like it's very concentrated around 200, and for the green, it's somewhere in the middle. So your measures of variability always give you a sense of the dispersion of the data around its center. Okay, let's go on. Now, variability is really, really important in many applications in data analytics, extremely important, especially for people that have like a supply chain bent. You would really appreciate what variability means. So let's go back to that graph. Let me give some examples that help us think about this. Now, imagine if we're considering these distributions as like, let's say office arrival times, right? Or the arrival time of a supply to your factory, right? So you run a business where you have a production line. Now, even if the averages are all the same, the process or the data set or the event that is on the yellow curve in sample C is much more predictable. The dispersion around the mean is much closer. So your expectation, even though this is the full range of possibilities, the expectation is very well centered around this minimum. So it's a very predictable process, right? Versus the blue line, what this means is if this is office arrival time, for example, on some days you come at 5 a.m., on other days like, midday. But on average, like we all come around 8 o'clock, plus or minus. The days were very early and the days were very late. That may just be horrible. You might prefer someone that even has a lower average time, but it's predictable. So it depends on the process. So you always have to think about data, not just in terms of the average, right? The measure of center, but also the dispersion around it, right? Just wanted to make that point. Think about Amazon delivery expected time, for example. Think about customer experience. If your Amazon delivery time is some days you're very early and people are, oh, my food came so fast, I'm really happy. But some days it's like so late that, it's pointless. Why did you even bother delivering my Uber Eats? And so the average is somewhere in the middle. But that could still be a horrible customer experience, right? If the expectation is so variable, it is so widely spread, it is so dispersed, right? Versus someone that comes not so early, it takes a long time, but the time they give is most likely the time, plus or minus a smaller range. So you have to think about variability in terms of impacts on processes, in terms of customer experience. There are lots of different things where you're showing the data, and it's important not just to show the center, but also variation around the center. This is sample variance. And once again, we've explained this. Now, remember, let's just pay attention here a bit. There's something I want to just highlight. So if you remember, here we looked at population and we looked at sample. Now, in inferential statistics, many times you don't have the whole population. Remember we said that, but you have to infer from the sample. And there's a long mathematical proof, but with sample variance, the denominator is n-1, right? As compared to for population variance, where you have the data points for the entire population, it's n. right? So for this class, I'll spare you the detail, but you just need to know this, right? And so remember, we talked about distributions. Well, we're all very familiar with distributions at this point. So these are distributions, and on the y-axis, remember, of a distribution curve is frequency, right? So standard deviation statistic is very intuitively applied to distributions and can show the range within which most of the data lies, right? Now, for a standard bell curve is also called a normal distribution, right? For a standard bell curve, and we'll talk about this later, we have empirical pointers that show that 95% of the data lies between two standard deviations around the mean. So first of all, so far, are we all good in terms of variability? Is there any question? Like, feel free to interrupt me, raise up your hand. If something is not really clear, just ask, right? Before we build on it. Right. So if you look at, follow me to the graph, the middle graph where there's normal distribution, right? So remember, we have a normal distribution. The middle point, this is a symmetrical distribution. The middle point is mu, or your mean. The middle is the mean. And we have standard deviation. We've seen what the formula is, the square root of variance. So there are empirical rules that show that around 34% of the data lies one standard deviation to the left of the mean, and one standard deviation to the right of the mean. Now, these are just standard empirical numbers for a bell curve. So what this means is you have 68% of the data lies around two standard deviations of the mean. So what this just means is, so if we had a distribution, let's go back to the previous graph. We have a distribution around 0. If the standard deviation of this was 25, right? What this means is that from 175 to 225, we would have 68% of the data. So if we had 100 customers, 68 of the customers are spending between $175 and $225. And that's the standard rule for the bell curve. The normal distribution curve is very common in many processes in nature. So many random processes are assumed to follow a normal distribution in many cases. So what we mean by that is, for many processes, right, we have around the mean a symmetrical distribution around the mean, such that you have about 68% of the data lies between one standard deviation less and one standard deviation more. And two standard deviations plus or minus, you have 95% of the data, right? So it's like 34%, one standard deviation, two standard deviations away, you have another 14%, and that way. So 95% of the data lies between two standard deviations of a bell curve. So what that means is, if you know the mean of a distribution of something that follows a bell distribution, a normal distribution, we'll talk about this some more. 95% of your data lies within two standard deviations. So if you know your standard deviation of the distribution, you know the mean, you can know where to expect about 95% of your data points. And this is really something to have in our minds, right? Because in many cases, at 95% of the data, you've covered like most of the probability of the numbers you're going to see within that distribution. And you could expand this thinking to lots of different things, right? But in practice, if you have a distribution, two standard deviations away on both ends of the mean, you have 95% of the data. It's important to note. And there's a rule of thumb, Chebyshev's rule, that just says at least 1 minus 1 over k square of the data points lie within k standard deviations. So if you're looking at two standard deviations, what percentage of the data are you going to get, and 3, and so on and so forth. Those numbers will closely tie to the numbers I've mentioned. All this is just to say the bulk of the data is concentrated within here to here, and you have outliers on both ends. And you can use Chebyshev's rule in lots of different applications. So for example, for a numerical data set, at least 75% or 3/4 of the data lies between two standard deviations of the mean, right? For this normal distribution, we can see it's about 68% of the mean and at least 88.9% within 3 standard deviations. So if you just plug the number of standard deviations as K in this formula, you can always get what that number is. Okay. The next thing we're going to look at is measures. Well, are we on the same page? Does anyone have a question? Okay, we're good. And if you have questions when you go back to look at this or you want some extra information, like just feel free to reach out or ask. Yeah, actually someone had a question last class and I got a link for them. Someone's asking how to pick samples, right? So I'm just going to share that link and put it in the chat before the class ends. It's a useful link that you can read on how to size your samples. And there's a practical example there as well. Okay, so the next thing we're going to look at is the coefficient of variation. So this is just the ratio of the standard deviation to the mean, right? Remember how to calculate standard deviation is square root of the variance. And when you divide that by the mean, you get the coefficient of variation. Very simple stuff, right? And all this means is a useful way of like comparing between different distributions. So if you want to look at the dispersion between more than one distribution, where the distributions are for different things, you want to say how dispersed is this distribution versus that. If you just use the standard deviation, you cannot compare different distributions, right? So these seem to be like for the same process, but imagine if we have another distribution that's for a different thing and the numbers could be much larger or much smaller, right? So you cannot compare like, oh, which is a more variable distribution, which distribution is more dispersed. But with the coefficient of variation, like it divides the mu, so it's like standardizing or regularizing the standard deviation as a measure or a statistic of dispersion, right? So this is just like regularizing it. So if you had a very large number, when you're dividing that variance and giving it relative to the mean, then you have numbers that be comparable. Sorry. Right, so it's useful for comparing dispersion in different data sets. But a major drawback is like as it tends to infinity, as the mean gets closer to 0. So if the mean is really small, then this number, coefficient of variation, gets really large and starts becoming meaningless, right? So the other thing I wanted us to look at as we get towards the end of our class today is covariance and correlation. So correlation is just like how the statistical association between two variables in terms of how they move together, whether in the same direction, in opposite directions, right? So covariance is a measure of joint variability of two variables. Covariance can take on values from negative infinity to infinity. At this point, like everything we've explained so far, is this straightforward? Is it clear? If there's any question, please feel free to raise your hand or drop something in the comments. So correlation, unlike covariance, correlation could be thought of as a standardized measure of joint variability and takes on values from -1 to +1. If we don't want to get too stats heavy, but just think about this as you're measuring the direction in which a certain variable moves. Two variables, are they positively correlated or negatively correlated, right? And think about it this way. Let's look at, for example, age and income. We can say there's a positive correlation between age and income, other factors being constant, right? So the older someone gets, let's say, the more growth they have in their career, the more senior they are, and the more income they make, right? So if you plotted age and income, let's say you have positive correlation, they're moving in the same direction. The variability is moving in the same direction. So negative correlation would be the reverse of that, right? So a good example I try to use is if you segmented this, what I just said, into two, right? So before retirement and after retirement. So after retirement, let's say people's income start going down, right? Or let's not use income. Let's say disposable cash, for example, right? It's going up. as you're getting more money. As you get old, let's say your medical expenses are increasing, but you're on a fixed pension, and so your disposable income is going down. So at that point, with age, the correlation is negative, right? Because you're getting older, age is increasing, but disposable income is going down. So just think about it. The sense in which two variables move, and you can use covariance or correlation. And correlation is -1 to 1. Covariance is negative infinity to positive infinity. Can be infinitely large. And there are just 3 diagrams at the bottom that just try to illustrate this. So negative correlation, positive correlation, no correlation. No correlation is where there's no obvious systematic relationship between the two covariates. And for no correlation, you will have this at 0. So if you're going -1 to +1, no correlation will be 0. And this is how you do it in Excel. Like, it's quite straightforward stuff. This is age and age, class, survive, ticket price. So a bunch of 4 variables and how, they correlate with each other. So you can see for the same variable, survived and survived is like perfect correlation. So like it's literally the same numbers. Class, correlation with survive. So I think this data is from, if I remember, the Titanic data set. So it's looking at the age, ticket price, and class versus survival in the Titanic, right? So here we can say the higher your class, the lower your chances of survival. Negative correlation. So that's how to think about correlation, and hope this makes sense. If you have any questions, this is the time. Otherwise, we can go on. Okay. Skewness, we've mentioned skewness here and there a bit already, and it's just a way to measure how skewed the data is in terms of its. Yeah, Roland has a question, please.
Sorry, I'm just curious. I mean, with the Titanic thing you talked about, so why is the higher class persons less likely to survive?
I don't know. I don't know. Is the short answer. Like maybe the higher class decks were lower, like nice, lovely cabins. I don't know. I have no idea. But there's something we'll talk about towards the end of the class today: correlation and causation. Okay. It may not be. It may just be some other random thing. Like I said, like maybe the higher classes were at a lower deck or something in the boat. We don't know for sure. Like it may not be something about the variables themselves. It may be like some other confounding variable, but correlation just tells you the direction in which the numbers move. There's a very popular saying in data analytics circles that correlation is not causation, right? So one may not be happening because of the other, but they're just statistically associated in this sense. Like, and that's what correlation and covariance show you. But that's a good question. Thanks. Yeah, please let's ask more questions. Like it helps us touch on different parts of the material, right? So skewness we've talked about a bit. It's just one way to measure it, mean minus median. Remember when I showed those graphs, those distributions, and how the skewness was moving the mean away from the median, and so this is just a way to measure that. But the idea remains the same. Right. So I have a few. Let's see, how much more do we have to do? Oh, yeah. So there are a few questions here. Like let's try and answer these before our class tomorrow. Like when I come, I'll just ask everyone. Like, please, these things, like just try and answer them. It helps you think through the concepts and know if you really got them, right? But they're like very straightforward stuff. Just check it, and we'll discuss it when we start class tomorrow. Yeah, so inferential statistics. So like all we've seen, right, so far, we're looking at like samples of data and we're trying to measure things about the sample. But remember that initial diagram we showed where we had population, we had sample, we had observation, right? So where do we access the material, please? I think it's been shared on Slack. So statistical inference you're trying to make generalizations or conclusions about the entire population, so that higher level based on the sample. And that's really important, right? Because, and that's the question, I've forgotten who asked me that yesterday about, okay, so how do you pick the sample? So there are lots of statistical concepts, right, that help you tie the conclusions or the things you're able to infer from the sample and tie it back to, okay, yeah, Jamaica is answering, and tie it back to the population, right? So a good example, which we've discussed a few times in this class, is polling, right? You want to know the election outcomes. You cannot check the entire population of the country of eligible voters. So you're taking a sample, right, to infer what the outcome of the elections would be from it, right? So distribution. So think about probability distribution. Probability distribution show possible values of a variable, right? And how likely those values are likely to occur in the population. So far we've been talking a lot about frequency distribution, like for a particular sample. And now think about probability distributions as if we take a sample and we have a distribution of that sample, it may not be the exact same in the population, but we have to start thinking about it in probabilistic terms because we know the distribution, frequency distribution within the sample and within the population, that probability of the likeliness of a particular outcome occurring in the population speaks to probability distribution, right? And you have a couple of different distributions. I won't go too deep into this, but just to tell you that with inferential statistics, we're trying to make generalizations on the population from what we can infer from and calculate statistically from the sample. I'll read a few things here. Binomial distributions used to model binary data, yes or no data, right? Very useful with drug trials, A/B testing. We have Poisson distributions. That's a bit trickier, but concerns events, right, that occur at a given rate. So there's a lot of like website conversions, like a lot of them follow that distribution. And not to bore us too much with all this, but just to mention it and to know that many times we work with normal distributions, which are continuous distributions. So with the continuous distributions, you have an infinite number. Remember continuous data? So you can see from the edges of those shapes, like they are not discrete. There's an infinite number of subdivisions within them, right? And we can standardize the normal distribution using the z-score. So the z-score just helps you standardize a normal distribution, right? So we can compare across data sets. And the z-score is just each observation minus, the z-score for a data point is just the observation minus the mean divided by the standard deviation. And you'll see how this is used down the line, but just for us to know this. Now, an estimator is a mathematical function that helps us measure with an approximate sense a particular parameter of a population from the sample. Remember, with inferential statistics, that's what we're trying to do, right? So just think about all the things we've been looking at, measures of center, measures of variability, those are all estimators. But in this context, we're trying to infer what's the mean age in a country from sampling a couple of people in that country? What's the likelihood of people voting for this particular candidate by sampling the eligible voters, a portion of them, right? So it's usually this single number that's based on your sample, but helps you represent that same statistic in the broader population. And the difference is, remember how I told you, think about the sample, you're thinking about your frequency distribution. In the population, you're thinking about probability distribution, because you're not measuring on the entire population. So whatever you measure in the sample, there's going to be an error, right? So you now start thinking about accuracy of the estimate. And that's why I highlighted here that you're looking at, so if the mean is X, for example, it's plus or minus an error. So there'll always be this error that accounts for the fact that you cannot measure accurately or calculate accurately that statistic for the entire population because you're working off a sample. And this is so practical because for most things in data analytics, you're going to be sampling like part of a bigger population, because you can either only make constraints of measurement, constraints of data availability, and all sorts of things, but you have to think about and understand these concepts. And these are stuff like that, more advanced topics, but things you should know and you will definitely end up using. So the estimator quality is measured on the mean squared error. It's one measure to measure it. And the mean squared error has two components. Just conceptually, look at this. Look at the diagram on the top right, right? Now, if the red is the value we're trying to estimate, right? If we have an estimate that's not dispersed, but is far from the mark, we say we have bias. So that's the systematic bias. So it's not correct, but it's well concentrated around the wrong number. Low variance, low bias. You can see the dispersion is low and it's not very wrong. It's right about the center. High variance, low bias. So you're not systematically away from the target, like what the real true number. Think about the red point as the true measure. So let's say this is the true standard deviation or the true mean. So bias is your distance from the middle, or how off you are in terms of the correct value, and dispersion is the variability you have. So the mean squared error, right, in inferential statistics will always have a variance component and a bias component. So the variance is the measure of spread of the estimate, and the bias is the distance from the true value. Now, the confidence interval, so the link I'm going to be sharing, like for sampling, always has to do with the confidence interval. The confidence interval is just, you're trying to set the limits or the boundaries of how certain, or the probability of the number, the estimate being within what the population parameter is, right? So if you want to be very, very certain of what you're measuring for the population, then most likely you need a larger sample, right? Especially if it's an effect that is very small, right? So if you want to measure an effect that's small, you're going to need a very large sample. So the confidence interval is just the probability that a population parameter falls between a value space of a certain number of times. So if you want a high probability that this measurement would always fall within in the population will always fall within the range you have, right? Then you're going to need a larger sample, for example. And the standard error is just a kind of way of standardizing things so that you have a standard deviation that pertains to the estimate of the population from sample. What we're just saying here is this. You always have the estimate and you have an error because you're not measuring the actual population, you're measuring a sample. And this is the formula for the standard error. Right. So I know we're pressed for time a bit. The last idea I just want to share with us, and from like in next class, we'll get to play with some numbers, right, in Excel and play with some of these things and then look at some Excel things as well. And we pretty much would have had like a foundation with which we can do lots of the case studies we're going to work on and a couple of interesting things down the line. But these foundational concepts are really important and you should go over the notes, go over the classes when you have the videos. Now, something we had mentioned earlier that I said we'll discuss later in the class is causality and correlation, right? So to the point of the Titanic data set where someone asks, like, what does class have to do with people's survival? And I said, no, it's not showing causality, it's just saying correlation, like those two variables are moving in the same direction. So causality refers to one event or variable being responsible for the occurrence of another. So it's like a direct, this is causing this, right? But with correlation, you're just saying like there's some association, there's a statistical association between these two variables. Doesn't mean one is causing the other. And this is really something important, something to note, because many times with business decision making, sometimes you're trying to find out what's driving this. That's a causality question. Did our marketing campaign result in more sales? Like you're trying to find out, did doing more marketing result in or drive more sales? And it's not enough to just say, when we had more marketing, did we have more sales? Like it's usually more nuanced than that, as we're going to see. But just remember, causality and correlation are two different things. One, causality is a direct cause and effect relationship, and correlation is just statistical association. Are they moving in the same direction, in opposite direction? Like, how does the variability of one variable relate to another? An example would be smoking causes lung cancer. Like, lots of studies, lots of research has shown a causal link between smoking and cancer. A correlation case would be, there's this data set I like we always refer to jokingly, like ice cream sales at a beach and shark attacks. And there's a correlation: more ice cream sales, when ice cream sales are high, shark attacks are high. But there's obviously no causal link. You cannot say shark attacks are driving ice cream sales or ice cream sales are driving shark attacks. The more we're selling ice cream, the more sharks are attacking. But obviously there's something else there, which is the temperature, the weather, right? So in summer, there are more people at the beach. Those people are buying ice cream because the weather is hot, obviously. And sharks also attack when there are more people at the beach, right? So you can see there's no causal link, but both things are correlated. And many times, especially when like you start thinking about building data science models or predictive analytics, different variables could have predictive power on a certain other variable without having a causal link, right? So for example, we could be able to predict shark attack volumes or occurrences based on ice cream sales, because the causal link has nothing to do with ice creams, of course, but there's some other confounding variable, which is number of people at the beach or number of people in the water, that has to do with another variable, which is the season of the year, temperature. But that said, both variables drive higher ice cream sales and higher shark attacks. So correlation could have predictive power on another variable without having causality. But that said, many times in business decisions, you need to be able to, for decision-making reasons, say if one variable is causing the other. And I'll just gloss over a lot of this area, but some relevant concepts to know in experiment design is conducting controlled experiments to be able to get this causal relationship. So the most reliable way of being able to establish causality many times is by experimentation. You want to design an experiment. And the reason for that is because you're able to control for different factors, right, that could confound or disturb, like you being able to establish that link. You have confounding variables, like that factors that distort the detection of measurement of causal links. I give one example with the high temperature, right? It's affecting both. If ice cream and shark attacks, if ice cream was a covariate and shark attack was our independent variable that we're trying to measure or estimate, temperature would be a confounding variable because it's just there. It affects ice cream sales and it affects shark attack, and the two have no causal link directly. The counterfactual just means, so if you're applying a treatment, let's say it's marketing, right? You have a couple of customers, you're going to be marketing, sending some marketing campaigns. The counterfactual is just, what would you have observed if you did not apply the treatment? So if you have a group of people and you send them marketing ads and you measure whether their sales goes up after the marketing ads, the counterfactual against which you would measure the increase in sales would be what would have happened if we did not market to these people. So these are just ideas to think about and to know as far as causality is concerned. Now, how do you prove causality quickly? I had mentioned experimentation, and the gold standard is randomized controlled trials. So randomized controlled trials, I just have a diagram that explains it. Very straightforward, but it's a concept we should all know, right? So let's pay attention. You have a population, you're splitting that population randomly into two groups. Now, the randomization is to account and control for other factors that are not the factors you're going to measure, right? So other factors that may have an effect, but by randomizing, you control for those so that you can focus on the factor you're going to measure. So in the one group, you apply an intervention. It could be anything, like it could be an experimental drug you give to one group, and to the other group, you give a placebo. Now, a placebo is just, if they're taking pills, for example, one pill is just nothing, white powder or Gary or whatever. And to the other group, you give the actual drug, like that you're trying to check its efficacy. And so the control group is just setting a benchmark against which you're going to be able to measure the effect of the intervention. So let's say this intervention is training people in Black Force, right? So random group of people, some are doing Black Force training, some you give no training, or you don't teach a particular part of the course, and that's your control group. To those you taught the thing you're trying to measure its effect, you look at the two samples and look at job rates between the two groups, the one where you taught the extra skill and the one you didn't teach the extra skill. So if they're the same, or if there's no statistically significant difference between both groups, then the intervention had no effect. And if there is, then it did have an effect, and you can measure that. Another pseudo experimental approach is difference in differences test. And what you just do in this case is, so think about it this way. Let's say in the same case where we talked about marketing, let's say these are two groups, the broken line and the green line. And these groups, this outcome is their sales, right? Monthly sales, like the purchases of the two groups. Now you have this trend that shows, because over time, like the sales are probably changing anyway, but you want to measure just the effect of your intervention, in this case, your marketing. So you have the trend of both groups. At this point 4, you do the marketing campaign and you want to measure the effect after. So this group, their sales go up, right? So how you measure the effect of the sales, what's the additional sales that our marketing campaign drew? In that case, it will be, if we did not administer the campaign, the assumption here is that the sales number would have been moving in tandem with the other group, because the groups are similar. So the first thing is to establish two similar groups. Over time, you have a trend, consistent. You have the intervention, and you have the effect. So the difference between the two lines, and remember the concept we said counterfactual. So this broken orange line is the counterfactual, which is what the trend would have been for the group you performed the intervention on if you did not perform the intervention. And so what you measure as the effect is just this to this. And these ideas, these methods are used in so many applications in data analytics. And I just thought like we should touch on this. Otherwise, our introductory part won't be complete. So we understand causality. Randomized control trials are the gold standard for being able to identify causal links. This is how they're conducted. You also have the difference in difference. That is a very well used method for determining the effect of an intervention. And this is conceptually how it's done, right? These are the key things you need. In the end, remember, the first idea is you need similar groups. There's a whole set of methods for determining similar groups, like propensity score matching and different things. But conceptually, it's still the same thing. You're trying to get two similar groups. You introduce the intervention and you measure the difference of that group relative to the counterfactual that you established based on your control group. So hope this helps us have a good foundation. Do we have any questions? Some people are asking about the notes. I'll share an updated version of the slide because I added a few things. And I also added the link to that sampling portion. So I'll just send to Jumoke the updated version of the slide so she could share it on the Slack channel. Do we have any questions before we wrap up for today? Any questions? Is there a group on Slack? Jumoke, could you answer like the housekeeping questions? I'm not too sure how things are organized. You can stop recording now.
Yes, there's a data analytics channel on Slack. I'll type in the name in the chat now.
Okay, thank you. So please let's remember